So we'll discussing about spectrogram, short-time Fourier transform, and its representation as a visual tool called the spectrogram. So what we had, let's just recap the important things. So we had this. We have a window. We have a signal which we call SM, beat signal. It could be anything, different upon different sounds. We put a window. This window could be of different types, of different lengths. We talked about how different types, styles, different forms of window, dome-shaped window and rectangular window, hemming, henning, and what are the advantages, disadvantages. So we have a window, and we place it of a particular length, whether you specify in number of sample points or in time. A particular length, you place it. The symmetric window. Remember, it's a symmetric window. The symmetric window is this L or some time, if you want to specify in time. So M. So this you put it at a point N. So if you go devise your basic signal processing, so scaling, shifting of signals. So you can write this, because the symmetric window, you can write it like this, or you can write it, both are the same. You can evaluate later. Both are the same, because this is a symmetric window. You can write it as m minus n or n minus m, whatever. So you have Sm and W n minus m, or Sm W m minus n. This is your speech frame centered at this point n. And then we take, if we take a Fourier transform of this, this is your short time Fourier transform. That is your short time Fourier transform. If you take the Fourier transform of this. Now, if you take the Fourier transform of this, as it is about j omega convolution. Please remember, this is circular convolution or periodic convolution. Why? If you revisit your signals and systems, you will understand, because for periodic signals, if you convolve periodic signals, you need to do periodic convolution, or also known as circular convolution. Now, what is this? Last time I mentioned it as W e to the power j omega, but it's a little, there is another term here. If you know your basic Fourier properties, so if Wm gives W e to the power j omega, then n minus m and m minus n is same. So let's take this, it's easier to understand. Wm minus n will be what? E to the power minus j omega n. So a particular frame, e to the power minus j omega n is a constant for a particular, if the frequency, you keep the frequency constant, evaluate for a particular frequency, n is the center of the frame, it's a constant, so it's a constant basically, and W e to the power j omega. That is how it is. So you convolve it this term. You convolve this with this term. Now, in the spectrogram, what the result we get from this, the main impact is from this term. This term does not have much of an impact. This term has an impact if you have revisited your signal system, something called linear phase. Means what happens is, suppose x of n is your signal, you have got x e to the power j omega. So what will happen? Xn minus some n naught. Okay, well, let's put it xm m minus m minus n. So that will be what? X e to the power j omega e to the power minus j omega n. So whatever shift happens in time domain by some amount, it comes up as a phase term. So it does not have much of an impact in the overall scheme of things. Whatever impact is there is because of the convolution of the window with the true spectrum of the speech signal, which we do not have access to. We only get to see the convolved spectrum when we do windowing and take the Fourier transform. But we do not have any option. Why we do not have option? We talked about it at length, and I hope you understand by now. You should be clear about these things. So one thing to remember, all this, it's a kind of a norm that we represent it in dB. Okay, so a 20 log of magnitude. So when you represent in use log, what happens is the small fluctuations you can see, and the large. So the property of log is if you have large numbers, it shrinks them, and if you have small numbers, it also brings to a comparable level. So uh, by using log, you are able to see the spectrum in a better way. It means in a log, if you take the log spectrum, you can see it in a better way. This is also called a log magnitude spectrum. What happens in speech for voiced sounds, for example, the formants, which we'll discuss today, the formants are, or the vocal tract resonances are very strong in the low frequency. So what happens is the entire spectrum, if you just simply take as c to the power j omega magnitude of that, uh, these values you do not see properly what is happening in this higher frequency region. In the log, if you take log magnitude spectrum, those things are reflected in a better way. So hence you can see what is the side lobe level and all those things. You can clearly see. Well, it's a kind of a almost customary thing that when we talk about magnitude spectrum, we always talk in terms of decibels. So going from that, so you have this, we discussed that uh, this is a wide band spectrogram, this is a narrow band spectrogram. Narrow band spectrogram has got horizontal striations. I think last time when I was speaking, even though I was saying horizon, showing you horizontal with my pen, I was speaking vertical. It happens because there is no feedback from your side. But I think I the following slides it cleared what I was trying to say. Horizontal striations for narrowband spectrogram and vertical striations for wideband spectrogram. And what is a spectrogram? It is basically uh, so you have the center of the frames. This is your time axis. Okay, this is your time axis. Uh, Time axis is your center of your frame, and for every frame you get a magnitude spectrum, log magnitude spectrum, let's say. So then you can represent this 3D plot, in terms of an image where your center frames are represented in the x-axis, frequency, in the y-axis, and this what is the value of your uh, uh, Fourier transform, windowed Fourier short time Fourier transform at a particular frequency for a particular frame. You just put those values in matrix form and then represent in a heat map or color code or even a grayscale. That's when you get a spectrogram. It's a very important visual tool. We discussed about all this. So now let's go to today's topic. Today's topic will be centered around one principal model or one principal concept or model by which we represent the speech production mechanism mathematically. That's called the source filter theory. Source filter theory. So why is it called the source filter theory? Because we will have an excitation source signal which excites or which passes through or which is input to a filter, that is a system, and that results in our speech. Now, how to model the excitation source and how to model the filter, that is what we will cover in today's class. So let's look at this diagram. This diagram we have seen in many forms now. You have air, we have this glottis, which houses the vocal folds. The vocal fold vibrates. Vocal folds vibrate when there is voice sound being uttered. Otherwise, it does not vibrate. It has no role. It's like a air going through, simply going through. So then you have this tube kind of different, of varying cross-sectional area. Then you have this tube of varying cross-sectional area, which we call the vocal tract. And the end of the vocal tract, then you have mostly we utter via our mouth or oral cavity through the lips, and this is the lips. And then for some specific sounds which we call nasal sounds, I am sure you have gone through all those videos we covered in previous lectures about how we classify sounds phonetically and under what criteria we use. For some sounds, air also comes out through the nose. But for mainly, this is what happens. Glottal vibration, either it occurs or not, passes through a tube. Based on different sounds, the tube structure will vary. It will be constricted in certain cases. It will not be constricted in certain cases. Then we exit through the lips. This is our main speech production mechanism. So now we'll try to model first the excitation, and then we'll see how to model the vocal tract and the lips. There's three things will be there. First, we'll have to model excitation, vocal tract, and then the lips. How are they modeled? That is what we will cover here. So these are the basic assumptions of speech processing we have been talking. Many of the slides that I am showing today, or in fact almost all of them, will be from Professor Ambika Raja's lecture slides from New South Wales, University of New South Wales, Australia. I have told you that beforehand. There's a wonderful slides he has, and even lectures available most probably in his platform. So basic assumption we have been is that all speech processing systems, the source of excitation or excitation and the vocal tract system are independent. So whatever is happening in the glottis, it does not affect the vocal tract. We call it decoupling. Yes, assume it. It's not really absolutely true, but more or less we go through that assumption. So hence we model excitation, vocal tract, and also the lips separately. So we have talked about it. The vocal tract can only change shape slowly. Cannot change at your muscles and tissues cannot move at infinite rate. Around this events mentioned 20 generally, yeah, around order of 20 millisecond. But significant change cannot occur in the order of in the voice production system. The significant change cannot occur for the order of around 20 to 50 milliseconds. For a time period of around 10 milliseconds, almost no change can occur in the vocal tract, but significant change over the whole voice production system, it cannot occur. It does not occur for around this time, and hence we use windows of generally we use windows of those lengths to analyze speech signals. Yeah, so now moving on. So how will we model? So first thing we'll do, if you remember, we'll talk about it again, but this part, if you remember, we used EGG signals, we measured glottal volume velocity. How did those curves look like? It looked like this. So what are these? These are basically puffs of air. Puffs of air. For every vibration of the glottal folds, there is like a puff of air being released, which then passes through the vocal tract system and finally produces sound, the speech signal. So we have to model this puff of air at the glottis. Now, for voice signals, we have this pitch. So this vibration occurs periodically. So we will use an impulse train having a particular pitch period, whatever is your pitch period, okay, or pitch frequency equal to, we'll put an impulse train, and if we pass that impulse train through a glottal pulse model, we say, okay, or GN in time domain, what will happen? This EN will be convolved with GN, okay, and this GN should be shaped like this, okay. Then at all these positions, 0, 0, whatever it is, N naught, or let's put it in time domain terms, T naught, 2 T naught, 3 T naught, okay. Whatever, at those locations, it will repeat. So we have to just find out what will be the transfer function which will give a shape like this in the time domain. Once we do that, then we have a vocal tract system. And here we'll find out why resonance happens, and finally we'll go for the lip radiation. So let's go first for the excitation source, how it is modeled. So as I said, if you have a pitch period, if your vocal folds vibrate, the pitch period, I say T naught, okay, here it is mentioned as P. So we can use a train of impulses. How is the train of impulses? This del n minus kt naught or pt naught, summation of en equal to, okay, it's a summation Now, how many times you do K, it depends. Depends on your frame size you have chosen. How many will be there in your frame? How many impulses will be there in your frame? Based on that, it will have the number of K will vary. Okay. So let's say if your frame size is, let's say, around 3 T naught, 3 times your pitch period. So 0, 1, 2, 3 maybe it will have. Okay, 0, 1, 2, 3. So that's how it is. So at those points, so this is your this is called your excitation train of impulses. So now we'll pass this through, and of course it will have your Z transform. You find out what your Z transform or Fourier transform of that is. But mention remember there is a train of impulses. Summation of K del of n minus kt naught. Okay, or kn naught, whatever you say, kn naught. In terms of sample points, it will be kn naught. Okay, so that's what it is. So now we will have to use a total pulse model which will give you some shape like this. So it turns out that, so if you see all of your windows, we have talked about those windows, it looks like a window kind of. And these windows, uh, if you look in the frequency domain, they are having low pass filter characteristics. The windows that we discussed, whether it be rectangular, Hamming, whatever, they're having low pass filter characteristics. You see, they have a main lobe near the origin, near frequency 0, and for a short time, short frequency range, they have a main lobe, and then they have side lobes which are very, very small. This is a characteristic of a low pass filter. So we found out that if we use Gz equal to 1 by 1 minus Az inverse whole square. That means there is a pole. Okay. So this is equal to Z by Z minus A whole square. Okay. So there is a 0 here at the center. And this A is nearly equal to 1 but less than. Okay, you can mention it like this. A is like this. So some real pole is here, but a multiplicity 2. There are a multiplicity 2. But let's analyze one of them. We have analyzed before all of a signal like this before. Okay, what happens is it comes out to be a decaying exponential, and you have two decaying exponential. You can see this, so you can break it up into 1 minus 1 minus a z inverse into 1 by 1 minus a z inverse. Okay, so this you say if you x1n, x2n. So what will, let me put, if you say g1z, z2z. So if it is multiplication in the z domain, what is in the time domain? Convolution. So z1n, z2n, convolve will give you g of n. And if you look at this, you will find, if you look at this signal, yes, if you look at this signal, you will find that it comes out to be almost like this. It comes out to be like this shape. This shape it comes out to be. And when you then use your train of impulses, okay, it comes up to be this shape. And in the time domain, in the after and if you see what happens. Let me show you. Yeah, this is the shape that comes out. And because I said is a low pass filter characteristics, it will have this kind of any window function. If you see, it looks like a low pass filter. So this also looks like a window. It will also have low pass filter, but a strong low pass filter characteristics. But in a time domain, it looks like this. So if you have En, which is a train of impulses, if you convolve with this G of n, and how is G of n given in the Z domain? It is a low pass filter. A 1 minus A is the inverse whole square. A nearly equal to 1. Okay, it is a low pass filter characteristics it has, and it results in this Gn results in time domain like this, like a window almost, asymmetric window, not a symmetric window, asymmetric window, and its frequency domain is, as we can see, it's a low pass characteristics. But we got in the time domain what we want, but and we when you convolve with a train of impulse, if you revisit your basic signal systems, wherever that impulse occurs, this will be replicated there. So this is how the excitation is modeled. Now let's go to, so finally you have En, this is the excitation process, modeling the excitation, En and Gn. On top of that, this we give a gain, okay, we give a gain to the excitation signal, this whatever we found, this excitation, total excitation signal, whatever we found, we give a gain, we just scale it by a certain amount. For certain sounds, you will utter at a higher energy, and for that reason only, nothing else. Certain other sounds, you will naturally have a softer energy associated with it. Loudness will be low. So this takes care of that, this fixed term A. So this is what finally we were talking about. Uh, you have for voice pitch. Here it is mentioned P means pitch period. You can take T naught or whatever. So it will be En equal to summation of some K del of N minus Kp or Kt naught, whatever you put. But mention that this is your pitch period. If you have voice pitch, and then you have a glottal pulse shaping model. And this glottal pulse shaping model is like this. In Gn is like this. Gz is has characteristics of a low pass filter. We talked about it. For unvoiced speech, there is the En, that is the excitation signal that is there, is not an impulse. We know because the glottal folds do not vibrate. It is a random noise. Here it is showing like this. It's basically a random noise. Okay. And because the glottal folds do not vibrate, this Gz equal to 1 for unvoiced. What does Gz equal to 1 means? That means Gn equal to delta n. So basically nothing happens. Just this the glottis is not involved in the process. If you put any input to a system, with delta n, what will be the output? It will be exactly. So basically, like the system is doing nothing. So in case of unvoiced speech, Gz is 1, or basically the glottis is not involved. Gn is delta n. So this random noise, En, is random noise. It just passes through the glottis without the glottis being involved in any shaping it in any form. And then we have this term that we multiply based on the loudness Every speech sound has some characteristics. Some are more loud, some are less loud. So based to take care of that, we have this gain term. It's a constant term for voiced or unvoiced. So this gives rise to your input signal at the glottis. So now let's go back. So what we have achieved, we've achieved this. We achieved this point. This is your input excitation signal. There is a model for the glottis. For voiced, for unvoiced, it is not there. Basically, del n or z is equal to 1. So we reach this point. This is the excitation after passing through the glottis, glottal excitation, you can say. This is impulse excitation or excitation source. And after passing through the glottis, it is glottal excitation. This will now, this puffs of air or simply a random noise like a flow of air will now pass through the vocal tract. So we will now model the vocal tract. So I have talked about so how the vocal tract is. At any time, if you take a snapshot, if you analyze this, is you will get your airflow here through the glottis, glottal excitation. The shape varies. Certain points you will have more cross-sectional area. Certain other points you will have less cross-sectional area. Now, in electromagnetic theory, EMT, or if you study viscosity and fluid dynamics, you will know that based on the length and width of the tube, length, width, height, all three, resonance occurs. What is the resonance? It depends on the length, width, and height of the tube. Or in case of a circular tube, cross-sectional area. In case of a circular tube. So because they are having different cross-sectional area, this is a tube which you can divide into equal segments of, but with varying cross-sectional area. And you will find where it is found that basically some of these tubes, all of them will produce resonance, but some of them produce very strong resonance effects. And that you can see in the speech spectrum at different frequencies. These frequencies are generally called vocal tract resonances or formants. Formants. So these high energy regions in the spectrum that occurs, it occurs because of this vocal tract which is having different cross-sectional area. If we analyze it for a short duration of time. Of course, for different sounds, this cross-sectional area and how the vocal tract shaped is varies. So we'll try to first model this for voice speech. So what we'll get is this vocal tract. What we have is a non-uniform acoustic tube is terminated, and cross-sectional area varies. Spectrum of the vocal tract consists of a number of vocal tract resonances, and these are called formants. For voice speech, I talked about it in the previous lecture. The magnitude of the lower formants is successively larger than the magnitude of the higher formants. But unvoiced speech, the opposite happens. The voice speech, the lower frequency formants have high energy. For unvoiced speech, the higher frequency formants have higher energy. Please keep that in mind, so that will change the way the vocal tract system parameters will be found, basically. So this is the representation voice speech. if you just somehow are able to just imagine you are able to segregate the information and find out the vocal tract resonance, the spectrum of the vocal tract, which is that or VZ. Okay, if we are able to plot the vocal tract spectrum, okay, V d about j omega, then this will be something. This is how it will look like. For unvoiced speech, this is how it will look like. Higher energy formants or higher energy vocal tract resonances. So now let's now model this. So we'll have, if you remember, uh, if you remember, we discussed what is the effect, how is a resonator resonance produced, and how is it modeled. So for any particular resonance, how is the tensor function? How does the tensor function look like? It's a pair of complex conjugate poles. Okay, let's take it P1, P1 star. If you have a pair of complex conjugate poles near the unit circle, a resonance is produced. Now we saw that there are multiple resonances. Generally, for every 1 kilohertz, there is a resonance. There is a resonance found in the speech spectrum. So we need basically for if I have 8 kilohertz signal, 8 kilohertz sampling rate. Yeah. So that means my spectrum is 4 kilohertz. Maximum is 4 kilohertz. So we'll need eight poles, complex conjugate poles, to represent uh, this vocal tract system. So what will basically the vocal tract system, we can model it like this. Based on a number of poles you have, okay, 1 minus pi z inverse, 1 minus pi star z inverse, where pi is a complex conjugate, a complex pole. This is how we'll model it. These are the number of resonances. If you put R, maybe number of resonances. So if you have 4 resonances, there will be 8 poles. But this is how we'll model our vocal tract system. Now let's go and check. Yeah. So this is how. Yeah. So basically, what happens is now you can simplify this equation and you can write in summation form. So it will be some 1 plus or 1 minus I equal to 1 to 2R. Okay. For one pair, it is a 2-degree equation. If you have 8 pairs, there will be 8-degree equation. 4 resonances, there will be 8-degree equation. 1 plus 2R, 1 minus some A or B. You put whatever you want. AI Z inverse. This will be the equation Z to the power minus, sorry, I. Or Z to the power I. Yeah, Z to the power minus I. Okay. Yeah. Or Z to the power minus K. Whatever you say. Or however you denote. So this is what is going to happen in a simplified form. This is your pole in terms of poles, how we represent. And if you simplify this, you have, oh no, sorry, you don't need this. 1 you have taken out. So it is 1 plus some AI Z to the power minus I. Or if you want to denote by K, A K Z to the power minus K. So it is a simplified equation that you will get. Sometimes you can also denote it by minus. It's a notational convenience, different books, different authors use this. But this is the form. It is a polynomial of order 2r, if the r is the number of resonators or resonances you have in your spectrum that you are modeling. So now, final thing is lips. So you will find, if you go through theory of EM, electromagnetic theory or viscosity fluid dynamics, whatever. Imagine, for example, you have a large container in your home. Will be a large water container, and you have a tap. Now, if your tap, this pipe is quite has a big cross sectional area, the water will flow out at less velocity. But if your it is very narrow, if your pipe is very narrow, your water will come out at high velocity. So just take this analogy. So what happens is this lips, because it's compared to your entire vocal tract, particularly the around your oral cavity or the mouth, it is quite big compared to your lips when you speak. So it acts as something like a high pass filter. And how can you model a high pass filter? This is how. Now 1 minus some BZ inverse you don't put it on the you don't model it on the where B nearly on the unit circle. If you model it's an unstable system, but so you don't do that. But somewhere B almost equal to 1. This is a high pass filter. If you analyze, this will come out as a high pass filter. Okay. So this is how we model the lips. So now let's put all of this together. Yeah, so lip radiation, if you take the frequency spectrum, r e to the power j omega, this will look like that. This is the phase, it's not bother about that. So what we have finally, we have impulse train, total pulse model. We put a gain based on the loudness. So we get this signal here. We have a vocal tract model, which is resonators. Then we have a lip radiation model. And finally, we get our speech. So this is the final in time domain material. En convolved with Gn, convolved with Vn, and finally convolved with Rn, lips. This is going to give you your speech sound. So it's like S of Z equal to AV, EZ, GZ, VZ, RZ. And now if you want to find out the transfer function, just from the excitation, you have your output signal and your excitation. This is your input. This is your excitation and this is your output. We have modeled this glottal pulse, vocal tract and radiation. We club this together as one system. And if you look at it from that perspective, the transfer function will come out as Z by EZ. The transfer function of the entire voice production system will come out to be as Z by EZ or AV, this AV, GZ, VZ, RZ. So this is what the transfer function is looking like. Here, what is GZ? 1 minus AZ inverse whole square, where A is nearly equal to 1. This is 1 minus BZ inverse, where B is nearly equal to 1. See, B and A are all nearly equal to 1. You can cancel, you can say that this effect is cancelled by one of these poles. So you can simplify. This is only 1 minus AZ inverse remaining. And this is your, obviously we just saw a vocal tract system. The entire thing you can club together in this form. Okay, entire thing if you can club together in this form. So you have 2R resonances. If you have R resonances, you will have a P here equal to 2R, and because there is another term here, your polynomial will increase by a polynomial will increase by another degree. So So this is your overall speech transfer function. Now in case of this is for voice speech. In case of and voice speech, GZ, I said it is 1, does not play any role. So it simplifies to just only your VZ and RZ is only present. So that's how our overall transfer function is modeled. Overall, it's you can simplify it as like this. You have a gain, and this is the basic overall, if you say, the voice production system model. So you use different values of Q here. If you based on the number of resonators, basically it will give you every resonator you will need 2 poles. So you calculate basically how many resonators you are modeling to represent your speech system. So that's it. That's all we have for today.